record the lesson. It seems to be working. Okay. As you know, we will speak about internal combustion engines, and the course will be organized into two parts. I will teach the first part of the course, which will be more focused on the, let's say, fundamentals of internal combustion engines. When I say fundamentals, I mean performance parameters calculation. How do we calculate or determine the main parameters which quantify whether an engine is performing in a proper way or not? We will speak about the combustion process of different engine technologies, and we will also speak about emissions and supercharging. The second part, which will be taught by Alessandro Brusa, researcher of our group of research, will be more focused on modeling, 0D modeling, or control-oriented modeling of engines. So in that part, you will be able to apply the theoretical knowledge we discussed during the first part of the course, add additional knowledge, and develop some, or at least study how it is possible to develop basic models of internal combustion engines. If I focus more the attention on module 1, the one we will discuss together, we can have a look at the contents. As you can see, the content is probably... Sorry. Okay, don't know what's happening, but it doesn't matter. The content is, let's say, wide. We will focus the attention at the very beginning on base contents. Maybe for some of you, you will find something which is not brand new, and in some cases you will see that there are some recalls from previous studies you already had in courses you attended during the bachelor degree. But the introduction is made to be sure that we are all on the very same page, and everyone is perfectly aligned, and we can start discussing more advanced concepts. Then we will study spark ignited, compression ignited engines. We will study the emissions from engines. We will study abnormal combustions, and we will also, and I think it will be an important part of the course, we will also focus the attention on some innovative combustion concepts like hydrogen engines and engines fed with synthetic e-fuels. We will see what they are. Maybe some of these terms are already familiar to some of you. In case they are good, maybe we will be able to go a little more in the details of these concepts. And for the ones who are not familiar, no problem. Of course, everything will be discussed in detail during the lessons. I wanted to share with you a bunch of information about the way in which the final examination will be carried out. The exam will be oral, let's say. I said let's say because it will be oral, but it will be a moment in which we ask you questions and you are able to write down an answer to our questions. So maybe you will have to demonstrate something, calculate something, and then we will discuss it together. So in this sense it will be oral, but you might be requested to write down something. So there will be 3 questions, and I already set the dates for the examinations. Here you see the dates for the summer session, and as you see, there is also a date for September in case you are not able to give the exam during the session of June, July. You can catch up in September. As I told you, at the end of each lesson, I will share what we produce during the lesson. So I will share the.
We can't hear you anymore.
You can't hear me? Can you hear me now? Can you hear me now? Can you hear me now? Can you hear me? Okay, I'll try this way. Can you hear me now? Oh. Okay, can you hear me now?
Yes. Yes.
Okay, I had some, I don't know, I had some problems with the connection of the room, but which is weird because I'm at the university, but it is what it is. Anyway, I told you, I don't know where you lost me, but I was talking about the dates for the exams, and I was mentioning the fact that there are 3 dates during the June-July session, and 1 if you have to catch up in September. As I was mentioning before, at the end of each lesson, I will share with you the notes of the lesson, and of course the notes will be shared in the platform you know as Virtuale. Probably you know that it exists. If you struggle to find the notes I share with you, just contact me via email, no problem at all. And the videos that I'm recording now, as you can see here, will be available in another platform which is named Panopto. Probably you don't know it because it's probably the 2nd semester of the 1st year, and you probably attended the 1st semester in Modena, which doesn't have these tools. But in case, again, you're not familiar and you struggle to find something, ask me via email again. Okay, normally, any question, any doubt, specific curiosity or something you didn't understand about what I said? If you want to ask now, feel free to do it. Okay, I guess there's no question. So I will proceed. Well, we are going to discuss. Normally, I like to interact with the students and ask you some questions, ask you your point of view about what we are doing, what we are discussing. One major concern I normally have when I start a course which is named Internal Combustion Engines is: does it still make sense to study internal combustion engines? You know that we are all focused in this period on decarbonization. So everybody is working to reduce the CO2 we have in the atmosphere, and if possible also to work on the pollutant emissions. We will see that emissions, pollutants, and CO2 are in some cases correlated, in some cases they are not at all. Okay, so we will see that carbon neutrality does not go always in the same direction in which emission limitations go. But in the past few years, sometimes I had some students which were a bit skeptical at the beginning of the course. So they asked me, they told me, we really don't know why we should still study engines, because they are a barely alive technology. So maybe we should focus the attention on something different. And unfortunately today we are online, so it's slightly more difficult to discuss this. But in case you want to say something, I'm more than available for a brief discussion, a quick discussion at the beginning of the course before starting this short introduction of the course. If you want to break the ice, we can talk together just a bit. Otherwise, no problem. Okay, no problem. Well, we will see that it's very difficult nowadays to start a course without to start a course which is an engineering course related to the description of a technology which is a power system, without considering sustainability as a major driver in the development of that technology. So we will try to do this, and we will try to discuss the technology, always keeping an eye on how it is complicated to be managed in terms of sustainability, how it can be much more sustainable, and how sustainable it can be compared to the alternatives we have. So this is more or less the sense of this introduction we are going to start now. We are trying to put engines in the proper perspective that we will have to maintain during the course, to consider the alternatives we have and we will have in the medium and long term as power systems for the automotive field, but also for other power systems in general. Why did I tell you that it's very difficult not to consider sustainability as something which has a strong influence on the development of a technology? Because this, the one you see here, was the concentration of CO2 we had in the atmosphere immediately before the Industrial Revolution. And according to the measurements we can perform now, it depends on the season, it depends on the place in which you perform the measurement in the atmosphere, but more or less this is the concentration of CO2. This number refers to 2023. As you can imagine, the number now is slightly higher than this one. Okay. We are seeing that this phenomenon is changing a lot the environment. It is affecting the climate. We see the consequences. We know that there will be effects in the long term, but nobody knows exactly where is the upper limit. Where should we stop this increase? Otherwise, the consequences are no longer manageable. Nobody really knows. What we can notice, these are open data I reported just as a curiosity for you. What we know is that the CO2 concentration is rocketing over the years, and while the CO2 concentration changes, we see that we have an increase in the average global temperature. Of course, there are peaks, there are oscillations, but the trend is difficult to not see as something extremely clear and strongly correlated to the CO2 concentration. We speak a lot about decarbonization, but what we see is that the production of carbon dioxide, which is considered the main reason why we are increasing the global temperature, is not going down over the years. As you can see in the right plot, in the right graph, the concentration of CO2 is still going up. Carbon dioxide is not the only reason why the global temperature is increasing. There are lots of greenhouse gases which are considered much less important than carbon dioxide because they are less present in the atmosphere. But the so-called global warming potential of other gases is much more dangerous than the global warming potential of carbon dioxide. We will see that other gases like methane, for example, or N2O are much more harmful compared to carbon dioxide for the global temperature. What we see also, if we have a look at the right graph, is that some countries or groups of countries started reducing the CO2 production over the years. You can see it, for example, for the European Union, but still they are emitting a lot. Other countries, normally countries which are growing now or which are developing their economy now, are producing much more CO2, and the CO2, for example, produced by China is rocketing over the years. As you can imagine, it's something that needs to be considered in a global strategy, because it's pretty obvious that we all share the same atmosphere. So the actions one country decides to put into practice need to be if possible, normally it's not so easy, coordinated with the actions which are put into practice by other important countries which produce a lot of CO2 as well. I wanted to ask you a question, just to understand what's your level of knowledge about these topics, and maybe if you are interested and you already read something about these topics. We are in a course now which is focused on the automotive field. So when we speak about automotive, normally we refer to applications which are designed for transportation. So what I ask you is, here we speak about CO2. We normally hear that there is a lot of concern about the emissions from transportation. We every day, more or less. Here, or maybe but it depends on probably on what you do in your life. But very often we hear expert saying that the solution for mobility, to decarbonize mobility, is this one. This is the holy grail which will make mobility carbon neutral. We heard a lot about, for example, how electric cars can save the world, how sustainable fuels can save the world, how hydrogen can save the world, making, for example, mobility carbon neutral. It's too early now to judge how meaningful these assumptions are, but I wanted to ask you, there is a lot of concern on mobility, but do you have any idea about the amount of CO2 which is produced by mobility compared to the whole amount of CO2 produced by human activities all around the world?
20-25%.
20-25%, which is not far from reality. Which is a good number, because if you consider mobility, this is not extremely up to date. It's from 2020, but as you can imagine, the picture nowadays is similar. Here you see the impact in terms of CO2 produced by transportation. And here we put together road transportation, aviation, and shipping. These numbers are nowadays a bit different. For example, shipping is in percentage a bit higher, aviation as well. The total portion for transportation is a bit higher than 16.2%, but in general, I think that this picture clarifies that if we concentrate only on road transportation and or aviation and shipping, and we forget about all the rest, so for example, energy using buildings, industry, and agriculture, we are in big trouble anyway. Personally, I think that over the past years we put a lot of emphasis on the fact that it was necessary to decarbonize transportation, and we also invested a lot of money, not always in the optimal, proper way, in the development of specific technologies without considering the goals and being technology neutral. We will see some additional considerations during the course. And we forgot a bit that even though we were able to set to zero this portion, overall the situation would be critical anyway. The main reason why we continue to emit more and more CO2 is quite simple, which is and it is strongly related to the growth of population. Of course, this rapid growth of population from the Industrial Revolution means that the Industrial Revolution and the developments we had later on led to wealth, and this is something which cannot be, I think it's pretty clear and straightforward. But this growth is becoming critical because we are changing the climate, and the climate is producing lots of heat waves worldwide, extreme weather phenomena. And what we see is that, in order to make it more practical, what's happening? Well, in the long term, sorry, in this slide I was a bit kidding. Probably you've seen the movie Don't Look Up. What's going to happen? Of course, in the long term, we are all going to die. But what's happening now? Now what we see is that the heat waves we have over the years always correspond to a higher number of deaths, which are directly correlated. So if we do not take into consideration these phenomena, and we neglect the fact that we are experiencing extreme weather events and extremely high temperatures, these phenomena kill people. So taking into consideration these problems and finding solution in the long term which can mitigate these phenomena are something which could be really beneficial for humanity. So in this sense, I think that we can, as engineers, feel the responsibility of doing something in this direction. The problem is that many times we say that we feel this responsibility, but all of us, or many of us, have different opinions about what the proper solutions which lead to beneficial results can be put into practice. Normally, when we speak about solutions, we hear people saying that we should all walk, we should use public transportation, or other people tend to say that using EVs can be the best way to mitigate the emissions, at least from mobility. Okay. I don't know what's your point of view. It's not necessary to discuss it now. On these first two solutions, let's say 1, 2. No. The highlighter is not fantastic, so this is 1, this is 2, and this is 3. 1 and 2, I have nothing to say. They are really sustainable options. If we walk or if we share the transportation systems with other people, we can reduce a lot our impact related to mobility. With this, I would say that it depends. It can be more sustainable or not. We will have to discuss it later on. But if we look at the technologies which are not related to walking or using public transportations, here I wanted to start introducing some major technologies we have for mobility. When we use a vehicle, we use a car, we are studying automotive engineering, so when we move a vehicle, we normally have 3 options in the short and long term. The option is to power the system with the internal combustion engine, or if we have an electric vehicle, we can use one electric motor, of course, plus the batteries, which store the energy, which are probably the most critical player in this framework. And then we have the so-called fuel cells. In this case, the propulsion system is still an electric motor, but the energy is stored in a fuel, which in most of the cases is hydrogen, especially for the most conventional fuel cells which are produced now, which are the PEM fuel cells. and basically they feed an electric motor generating electricity, converting a fuel, as I said, normally hydrogen, into electricity. So these are the three options we have available for mobility in automotive vehicles. Well, again, unfortunately we are not together in class. I ask you a question if you want to answer, otherwise we will have any other opportunities to discuss it. Do you already have a point of view? Is one of these three options better than the other in terms of sustainability, weaknesses, strong aspects? Do you have an opinion about this? Okay. Again, it's too early now to go in the details, but we will see that each of these technologies are, maybe this is surprising for you, but we will see during the course that these technologies are not that far one from the other in terms of carbon impact. And the most sustainable technology for propulsion, internal combustion engines, electric motors plus batteries and fuel cells, each of these is sustainable or not depending on where and when you produce and use that specific technology. Maybe it could sound weird, because some might say, how can electric motors and batteries be less sustainable than a spark ignited engine? They do not emit anything. I see lots of Teslas going around in the city center, and they are silent. They do not produce any pollution. So they look perfectly sustainable. We will see that there are other aspects, maybe some of you again are already aware about that, which need to be taken into consideration when we perform what is normally called a life cycle assessment. So when we analyze the impact of a specific technology from its production to its recycling stage. So in some cases, we tend to think that the future is fully electric, and some say that electric cars will be the future of mobility. I have to say that in the long term, it is difficult to see what's going to happen. We really don't know what's going to happen in the future, because the technologies we were mentioning before, these three, are developing a lot, and they are becoming more and more efficient over the years. So maybe the comparisons we are performing now will lead to completely different conclusions in, I don't know, 20, 30 years. But at the moment, the short-term future struggles to be fully electric for several reasons. So some experts in this field normally are starting to say that probably the future will be eclectic, not electric. Eclectic in the sense that mobility will be probably based on a mix of technologies, which will combine in the vehicles of the future internal combustion engines and electrification. Unfortunately, again, I cannot see your faces today. Maybe some of you are skeptical, but again, we will see it. I'm going to conclude this introduction with some examples. Over the past years, I read a lot of times that combustion engines were dead. Here I reported some titles from magazines or newspapers in which I read that in a couple of years internal combustion engines would have been banned, about the fact that several manufacturers were going to electrify their fleets in very few years. And remember that electrifying does not mean going full electric. And we also know that in 2035, theoretically, it will be no longer possible to produce cars which are equipped with internal combustion engines fed with fossil fuels in the European Union. We will see what's going to happen. But the point is, engines are still here, and there are some technical reasons we will see during the course, and which I think, when we will do some energy balances, will convince us. And these technical reasons are not related to conspiracy or any other theory which some people tend to use or to mention sometimes. So who's more climate friendly? A car with an electric motor or one with an internal combustion engine? Again, it depends. Of course, this picture might look a bit stupid, but of course it's a joke, which basically wants to focus the attention that diesel cars, for example, are considered evil at the moment because of several reasons. Some of these reasons are perfectly meaningful. For example, the Dieselgate is one of the reasons which shed a lot of bad light on internal combustion engines. And of course, these cars are considered high polluting cars. Okay. Normally, we consider electric cars extremely clean. So we consider EVs, electric vehicles, as totally clean because they do not produce any pollutant from the tailpipe. What's the problem? The problem is that the real impact of electric cars depends on the way in which we produce the energy which is introduced in the car. And for this reason, I read a book of an engineer who was mentioning, you know what the EV means? It's electric vehicle. I read a book about an engineer who tended to name EVs as EEVs, which in his perspective was the acronym of Elsewhere Emitting Vehicles. Because honestly, they really produce emissions normally, but they produce emissions somewhere else compared to where they are used. Of course, it is pretty obvious, the amount of emissions they produce depends on the way in which the electric energy is produced. if the energy is produced using renewable sources, of course the impact of these technologies is very low. If the energy is produced from burning fossil fuels, as you can imagine, the impact becomes extremely high, because even though they are normally efficient, the process which is behind the production of electricity is not that efficient. Okay, so overall their impact increases a lot, but it depends on the energy grid in which these vehicles are charged. Of course, it depends also on the country. Here are some examples. It depends on the season of the year. Probably you know that in Italy, at least during the summer, 60 point something % of the electricity we produce during the summer is renewable, and of course during the winter it is much lower. So the season of the year in which we use each specific technology is very important to quantify the real impact of that technology. And when we compare different technologies, engines for example, and other vehicles which do not produce emissions from the tailpipe, we also have to change the control volume in which we quantify the energy usage and the emissions. Because, for example, electric vehicles, as we said, are charged using electricity. Electricity might be produced using an industry. And of course, when we quantify the impact of each technology, we have to consider the proper control volume. Because the vehicle is no longer enough. Just to give you an example, this picture is taken from a paper I read a few years ago. It was an evaluation of a comparison in Europe between the CO2 emissions associated to battery electric vehicles and gasoline powered car with an internal combustion engine, and another car, the same car equipped with an engine fueled with diesel, so a compression ignited engine. Well, as you can see, there are some differences. The usage was considered up to 200,000 kilometers, so this was the expected life for the vehicle. And as you can see, again, it's not necessary that you know this, but we will discuss it better in the future. The green line corresponds to the car fueled with gasoline. And as you can see, it is the one that produces the highest amount of CO2. And if we compare it to the red trace, which is corresponding to the emissions from a car which is equipped with an engine fueled with diesel, so a compression ignited engine, it is less efficient. It produces more CO2, and this is normally associated to the fact that when we move from spark ignited to compression ignited engines, normally we have an efficiency gain which is around 6 to 10%. So normally this advantage, sorry, I am admitting a colleague of yours. Okay, when we move from spark ignited to compression ignited engines, we gain efficiency, so we reduce CO2 emissions. But what you see, which was extremely surprising for me at the very beginning when I read this paper, is that electric vehicles started their life with an amount of CO2 associated with the vehicle itself, which was much higher compared to the starting point of cars equipped with internal combustion engines. And the main reason why this line was starting in this point was simply one, and it was the battery. Producing a battery for a battery electric vehicle is extremely energy consuming. So the extra CO2 associated to the production of the vehicle is similar to the emission increase or the CO2 production you have in a diesel vehicle after running the car for approximately 50,000 kilometers, which was at the beginning for me quite surprising. Then you start from this point, and if you consider the energy grid we have in Europe, average, you see that the rate of increase of this line is actually lower. So if you recharge the vehicle, you produce less emissions, but the main weakness is the production of the battery. Obviously, this slope is not the same in the US, in Japan, in Asia, or in other countries. So this is what you have if you recharge the vehicle in the European energy grid. Again, the only goal of this is becoming aware of one simple thing. The problem is complicated, so we cannot draw conclusions which are that cutthroat, because the situation is complicated. Finding the best technologies depend on the applications normally, and we will see that all the certainties that some people have are not that easy to justify in most of the cases. Anyway, we have some alternatives, we have some technologies available, we are developing these technologies, and we have some goals. Which goals do we have? Probably most of you are aware.
Sorry, just for curiosity.
Yes.
The step that was in the...
Sorry, I have the audio coming from two sources. Okay, repeat please. Sorry, was my bad.
In the precedent slide, we had like a step after, I think, 100.
This one. I think this no longer exists, because this was in this case the battery was replaced with another battery, because as you can see, this extra increase is the same you have here, and the reason was that after 150,000 kilometers or slightly more, the battery was no longer the capacity of the battery was low enough to replace the battery. Now I have to say that the battery technologies have been improved a lot, and it's normally in a battery electric vehicle the battery is guaranteed for approximately roughly 190,000 kilometers more or less, which means that after 190,000 kilometers the battery capacity is higher than 70% of the initial battery capacity. So probably this number should be here. This replacement should be here instead of here, but the physical meaning of this step is the one I was mentioning before. I don't know if I answered.
Yeah, thank you. Or just a curiosity.
Yeah. Feel free, again, as I told you, to ask.
Can I ask another question?
Yes, of course.
So the usage of EVs might be helpful or less helpful depending on the country we are in and how much so the slope of the curve changes every time.
Yes, if you go to the US, for example, the yellow line does not go up with this slope, but it goes up like this. I mean, it's not, I don't know if it is exactly like this, but it is higher because the fraction of renewable energy production we have in Europe is higher. So it means that normally, if you connect an electric vehicle to our electric network to charge it, you are more sustainable than if you connect the same vehicle to another grid.
Yeah, and the point was that maybe, so if more energy is produced by renewable sources, the starting point of CO2 emission also changes, or does remain the same?
You mean this?
Because part of manufacturing CO2 emission also depend on how energy is produced, right?
Yes, but most of the energy most of the CO2 production, which is related to the production of the battery, is not has nothing to do with the energy grid you have, for example, in Europe or in the US. I mentioned this because I'm together with my group of research, we started to work on some specific analysis in this field, which are named LCAs. So LCA means life cycle analysis, which is an extremely complicated work, because you try to take a vehicle and rebuild, going backward, all the different sources of CO2 you had during the manufacturing process. In most of the cases, what makes this step so significant is related to the extraction of the rare earth elements, of the lithium, of the components you need to create the battery. And these components normally are not extracted in Europe. They are extracted in countries in which the electric grid is...
So countries where the energy cost is really low, but energy is produced by non-renewable sources, like China, for example.
Exactly.
Okay, got it.
Or Africa, or other places.
Thank you very much.
So we are just starting with this overview to try to collect some information and then be more aware of the problems when we will discuss sustainable engines or the weaknesses of current engine technologies. We said that we have some goals, and the major goal we have is to be carbon neutral in 2050, 2055. Sometimes it depends on the goals we are considering. But as you see, we are, at least this graph refers to Europe, we are going in the right direction. I'm not sure we are in the proper direction to go to become neutral in 2050. With regard to the automotive field and transportation, probably you know it, I'm not sure, but probably you know that we have to be carbon neutral from 2035 onward, which means that in the European Union, according to the current regulations, in 2035, only carbon neutral vehicles will be sold. Of course, the non-carbon neutral vehicles will be used because they will be already on the market, but from 2035 only the carbon neutral vehicles will be produced, which means that a carbon neutral vehicle is a vehicle which does not produce any CO2 emission when it is used. So it means that if you burn a fossil fuel, you have you burn a hydrocarbon. Again, we will see it, but probably you know that current vehicles burn hydrocarbons. So when you have this molecule of a hydrocarbon, you have carbon and hydrogen. When you burn this, of course, you produce CO2 and water. We will see the reactions, no problem. But now it's just to focus the attention on this. When you burn a hydrocarbon, of course, you produce CO2. If the hydrocarbon comes from a fossil source, nature took a million of years to produce it, and now we burn it and we produce a lot of CO2 in the atmosphere. So this process cannot be sustainable. We increase the CO2 concentration in the atmosphere, so according to the current regulations, from 2035 onward, these vehicles will be no longer acceptable. So which alternatives do we have? The alternatives we have are battery electric vehicles. Of course, they do not produce CO2 from the tailpipe. We have hydrogen. If you burn hydrogen, you do not produce CO2 because in the molecule you don't have any carbon. Or we have hydrocarbons. The hydrocarbons are the so-called e-fuels. Probably you heard this definition. Maybe you are not extremely aware of what they are, but there's a lot of research at the moment on this topic. These e-fuels are synthetic fuels which are produced from electricity, and if the electricity which is used to produce these e-fuels is sustainable, renewable, using renewable electricity we are able to take carbon from the atmosphere, create hydrogen, put carbon and hydrogen together, and when we burn that molecule we produce again CO2 which has been previously captured from the atmosphere. So the overall balance of this process is net zero. So if you capture using renewable energy and create a molecule and burn again and reproduce again CO2, overall you do not increase the CO2 emissions in the CO2 concentration in the atmosphere.
Sorry. Why do regulation that consider only the tailpipe emissions and not also an enlarged control volume, as you said before? Because it doesn't only come from the tailpipe, but also from the production and so on.
This is a very good question, and the answer is that they are poor. They are old, and they are currently under development. They are being updated. But at the moment, they are extremely weak, and they are not fair in the comparison of the different technologies. And this is exactly the reason why at the moment we don't have a fair emission regulation which is good enough to give the same importance or to quantify the impact of all the vehicles we have on the market. At the moment, the emission regulations we have lack from homogeneity in the quantification of the impact of the different vehicles. Extremely honestly, I would answer this. and we will see that quite a lot of work is being done at the moment to develop new emission regulations, but we will see that it is not so easy because, again, it's complicated, and preparing let's say well to wheel. Now we have emission regulations which are named tank to wheel, TTW, which means tank to wheel, which means that they quantify the energy losses we have going from the tank of the vehicle to the wheels. So we start here and we arrive here. Fair emission regulations should be the so-called well-to-wheel. So from where we take the energy to where we use the energy. Now lots of regulations are under development, but at the moment we are stuck in an intermediate situation. But the question was super correct, because the last thing I wanted to analyze with you is this consideration, this question. How do we measure the emissions of a vehicle? And this is a key problem which is related to the question I just received. The obvious place to look is the tailpipe. And when I say obvious, I mean that the current emission regulations look at the tailpipe. But there's much more to it than that. Before you drive a car, it must be built, and to build it, resources must be extracted. And on the other side, which is an even more complicated aspect, what happens when the vehicle reaches its end of life? Before I mentioned the fact that it's very difficult to go backwards and, for example, quantify the CO2 emissions associated to the production of the batteries. But quantifying the emissions associated to the recycling of old batteries is even more complicated, because now we are in a stage in which we are using electric vehicles produced in the past few years, but we are not yet completely available of how we will be, or we are not completely aware of how we will be able to manage all these batteries when they will have reached their end of life. So adding the electric vehicles to the mix, which is a reasonably recent problem, we also need to completely decarbonize the electricity generation. So if we want to properly quantify the emissions, and we really want to decarbonize transportation, which is the goal we really have, because we said already that it is necessary to do it because of several reasons we see every day in how the quality of the air and climate are changing, we really have to do it with a fair approach, which does not give favors to a specific technology compared to another one. I mean, I'm not in favor of one compared to the other, but I think that as engineers, we really have to be fair in doing these considerations. So when we look at the conventional engines, we have to say, okay, it's rubbish because it uses, in most of the cases, fuels which come from fossil sources, and they have a reasonably low efficiency. Okay, but what about the alternatives? The alternatives are that strong how do we produce electricity, how efficient are we in the production of a battery, what's the amount of pollutants we produce when we manufacture a battery. So we have simply to analyze all the different aspects and draw some engineering conclusions, which are sometimes different from the common sense we have in our society, and also different from the actions which are taken by our politicians. But again, as I told you, we just have to collect information, put everything together, and understand how complex the situation is. Okay, this was just an introduction, and I really wanted to do it together to start collecting some useful consideration information, which are, in my opinion, necessary to look at engines in a different way. We will sometimes recall this consideration, and also we will go more in the details during the course. I would stop here for a short break, and then after the break we will start to go really into the study of internal combustion engines. If you have any question, I am of course available. Feel free to ask. Otherwise, we have a small break, like, I don't know, 5 to 10 minutes, and then we will start again for the second stint of the lesson.
Excuse me, Professor. Sorry. Are the slides and the lessons uploaded in the 2025 folder of the course? Because I found the 2024 one, but it's they're not the same. So
no, they're not the same, and the course will be a bit different. So not yet, because normally I upload the slides after the lesson. But if you prefer to have the lessons in advance, I will try to do it from next time. I will try to upload everything before the lesson.
Thank you very much.
Okay, so let's have a bit of a break, and we will start in 5 to 10 minutes. Okay, so I think we can restart the lesson. You should be able to hear me again. And well, in case something is not working, let me know, otherwise I proceed. Okay, let's start from the very basic concepts of internal combustion engines. During the course, we will study internal combustion engines which are characterized by the presence or the implementation of the so-called four-stroke process. So we will have engines which are in most of the cases characterized by a cycle that can be divided into 4 consecutive strokes. Again, probably some of these concepts are very well known to you, but in case you have any doubt, please stop me and feel free to ask. The first stroke is the intake stroke, where we introduce the air inside the cylinder. As you can see here, there is an intake valve which is open, and in this stroke the fresh air enters the cylinder. The piston moves from the top to the bottom dead center, rotating the crank slider mechanism around the crankshaft. Then the piston reaches the bottom dead center, and during the compression stroke the piston goes up and moves from the bottom to the top dead center. As a result of this movement, in the first stroke, which goes from approximately 0 to 180, the pressure inside the cylinder remains low, close to the atmospheric pressure. The valve is open. Then, approximately here at 180, you close the intake valve, and with the valves closed, you move the piston up and you increase the pressure inside the cylinder. So the piston approaches the top dead center, and while it approaches the top dead center, somewhere in a point which is close to the top dead center, you have the so-called start of combustion. So if the charge within the cylinder did not burn, or if the charge within the cylinder were not ignited, we would have in the cylinder the blue trace pressure. So we would have the intake, compression and expansion, and in this case the engine would behave more or less as a volumetric pump. Here what you see is that in the real world we have an extra pressure increase, which is the red trace added to the blue one, which leads to the instantaneous pressure that we have within the cylinder, because the compression expansion blue trace is increased by the fact that within the cylinder we have a charge which also contains a fuel which is ignited, and the extra pressure we generate pushes the piston down from the top dead center to the bottom dead center. During this stroke, we really collect energy, work. Then when we approach the bottom dead center, we open somewhere here the exhaust valve, this one, and then the exhaust gases leave the cylinder and go to the exhaust line and leave the engine. Of course, they do not immediately leave the engine because, as you know, there are some post-processing tools like, for example, the after-treatment systems, which have to process the exhaust gases in order to minimize the emissions which are released in the atmosphere. So if we consider this 4-stroke process, and if we look at its consequences on the in-cylinder pressure trace, what we see is that each cylinder produces a pressure within the cylinder which is the sum of the motoring pressure, which is the compression expansion trace, plus an extra pressure which is basically related to the fact that we are burning fuel and we are generating an extra pressure which really delivers the positive effect of the engine. So to see it in another way, we have 4 strokes, but the only one in which we really collect power is this one. Or at least the only one in which we collect a significant amount of power. So this is the process. How do we study the process from a thermodynamic point of view? Well, we have different ways. The most typical and easy way is to use an ideal cycle or start from an ideal cycle. Normally the Sabate cycle is the most common way we have to study the efficiency of an internal combustion engine, and it is an ideal cycle which combines two simpler ideal cycles, which are the Otto cycle and the diesel cycle. The Otto cycle is an ideal cycle in which we have one ideal compression which goes from 1 to 2, and then we have an ideal combustion. I don't remember what I said. The Otto cycle, let's start from this. We have this ideal compression, and then we have a combustion which takes place at constant volume. While the diesel cycle is similar, but the combustion process takes place at constant pressure. Then in both cases we have an ideal expansion, which is the one that in this case goes from 4 to 5. The Sabate cycle puts together the characteristics of these two ideal cycles. Okay, just to clarify it a bit better, let's have a look at this. We said we have ideal cycles, okay? So let's try to prepare or to create together the indicator diagram of one of these two ideal cycles. The indicator diagram is the diagram in which we have pressure and volume, or pressure as a function of the volume. All the engines we described before are characterized by a minimum and a maximum volume, where the minimum volume is the volume of the combustion chamber, VCC. We can name it in different ways, but the minimum volume we have in the cylinder when the piston is at the top, dead center. Okay? So when the piston is up, at the top, dead center, we have a certain minimum volume, which is the volume of the combustion chamber, and which of course cannot be set to 0. Then we also have a maximum volume, which is VCC plus VD, where VCC, as we said, is the volume of the combustion chamber, and VD is the displaced volume. So here we have one minimum pressure, which is something around what we have when we start the compression, so when we close the intake valve. Then we have an ideal compression, like this, and for example in the Otto cycle which is, as we said, ideal. We have a compression that goes from 1 to 2, and then we have a combustion, which is an energy introduction, which takes place at constant volume, okay, and which goes, for example, from 2 to 3. The expansion, again, is ideal. And when I say ideal, is that I mean that 1-2, this compression, is an ideal compression, and in this case the gas is ideal, the transformation is isentropic. So the equation we can use to represent this compression is P times V at gamma is equal to a constant, where gamma is the specific heat ratio Cp divided by Cv of the ideal gas, approximately 1.4 for air as an ideal gas. Okay, I think it's pretty simple, and it was pretty clear for you all. If we consider the diesel cycle, it is always an ideal cycle, but the way in which we introduce heat is different. We introduce heat at constant pressure, and then we have again an ideal isentropic expansion. This is how we introduce heat. This is how we introduce heat. Again, the Sabate cycle puts together these two cycles. Okay. So let's go back very quickly to our slides. We can start introducing some, again, quantities you probably already know, you already heard in the past. You already studied in other courses, but it's very important to be sure that you all have clear these quantities, because these quantities are the ones which are really correlated with the performance of the engine. What do I mean when I say that they are related to the performance of the engine? I mean that if you will in the future develop an engine in your activity, or you will assess the performance of an engine, or you will study how efficient it is, or you will do anything which is related to engines in motorsport or in other more conventional industries or applications, you will have to analyze the amount of work which is produced by the engine, and in most of the cases you will refer to the indicated work produced by the engine, which is the integral of the product P times dV, where P is the in-cylinder pressure and V in the volume of the cylinder, so the product between the pressure and the variation of the volume, and the indicated mean effective pressure. Again, this is indicated and this is indicated because they both depend on the in-cylinder pressure. Everything which is related to the measurement of the in-cylinder pressure is an indicated quantity. The indicated mean effective pressure is the so-called IMEP, and it is the ratio between the indicated work and the displaced volume of the engine. The ratio between the two in terms of dimensions is a pressure, so it's the reason why this quantity is named indicated mean effective pressure. It's a sort of, let's say, work normalized with respect to the engine size. So normalized with respect to the engine displacement. Okay.
Could you explain again what indicated stands for?
Indicated is just a name which is used every time we are mentioning a performance parameter which is related to the measurement of the in-cylinder pressure signal. If you look at this indicated work, it depends on the in-cylinder pressure. So it depends on this quantity which is represented here in black. If you measure the pressure, you can calculate this quantity. And we will see that there is the indicated work. We will see that there is the so-called indicated torque. We will calculate, not today, but maybe next time. And these quantities are extremely important, because when we develop an engine and we try to maximize its performance, normally we test solutions which impact the combustion process, and normally we analyze the impact of each technical solution on the combustion process, measuring in a test cell the in-cylinder pressure signal. If you measure the in-cylinder pressure signal, you are able to quantify the effect on the combustion process of each modification you put into practice. Okay? And if you calculate this integral, and you calculate the indicated work, you immediately see that this work corresponds to the area which is included in this indicator diagram. There is normally a distinction in engines between indicated quantities, so indicated something, and brake quantities. So for example, we have indicated torque and we have the brake torque. Why? Because the indicated torque is the torque calculated from the in-cylinder pressure. So it depends on the combustion process. The brake torque is the torque which is measured available at the crankshaft of the engine. So in the middle between indicated torque and brake torque, there are other losses. So there are, for example, the friction losses you have, the pumping losses you have in an engine, okay? So if you want to analyze the impact of a certain modification on, for example, the spark plug you use, maybe you will see that there is an impact on the combustion process and you will see that effect on the indicated quantities. If you test, for example, a different lubricant or a different oil for the engine, you will see that you change the frictions, so maybe the indicated quantities remain identical, but you increase anyway the brake torque because you reduce the frictions. I don't know if I answered your question.
Yes, thank you.
Okay. So these are two key parameters. Then another aspect which is normally largely studied in your base courses, but based on my experience, not everybody did it, so probably it's the case to spend a few time remarking the importance of this, is the so-called thermal efficiency. The thermal efficiency is the work we get, the indicated work in this case, from a propulsion system divided by the energy available for the system. Okay, so in this case we divide the work by the energy budget we provide. So in this case the energy budget is the mass of fuel times QLHV, which is the lower heating value. Okay, if you consider the lower heating value, LHV, lower heating value. The lower heating value is a characteristic of the fuel. It's measured in megajoules per kilogram. So it's the amount of energy contained in 1 kilogram of fuel. Do you know, for example, what's the typical value of the, more or less, as a rule of, I mean, roughly, what's the lower heating value of a conventional fuel which is used in an internal combustion engine, for example, gasoline or diesel?
48 megajoule kilogram.
Yeah, 48 is quite a lot, but 43 is more common. 43 megajoules per kilogram corresponds to gasoline or diesel. And if we look at this number, I don't know if you have an idea, but 43 megajoules per kilogram is a lot of energy in 1 kilogram. And here we see one of the major issues related to the use of battery electric vehicles. The problem is that it's extremely difficult to have all this energy in this weight. Consider that in order to store the same energy, if you consider a new battery, I mean technologically advanced lithium-ion battery, the weight you need to store the energy that you have in 1 kilogram of fuel is normally corresponding to a mass of battery which is 12 to 15 times higher than the mass you need to store the same energy in a liquid fuel. Just to give you an idea. So the reason why in electric vehicles you say that the range is a problem is exactly related to the energy density that you can store in a battery compared to the energy density that you have in a liquid fuel like gasoline or diesel. Some might say, okay, but we do not need that energy density. We just need to have a recharging station in order to recharge very often our vehicles. Yes, but consider that, I don't know if you are aware also of this, but at the moment in Italy, for example, we have like 22,000 gas stations where we can fill the tank of our cars, and we have more or less 50,000 charging stations for electric vehicles. Anyway, it is still a problem because there's not just the fact that we have more energy in a specific mass. There's also the fact that charging of energy with a liquid fuel a vehicle is very quick, while charging a battery electric vehicle is much more complicated because it's difficult to have the high power we have in introducing the energy within the tank. Normally, when you charge a vehicle, you use powers, electric powers, like which range between 1 to 50 kilowatts. The flux of power you have using a liquid fuel from the pump to the tank normally corresponds to a power flux which is in the order of the megawatts of power. So this is another difference which goes in the direction of making easier to use vehicles which are powered with liquid fuels. Okay, so the energy, we were saying, the energy we have is the product between the mass of fuel in kilograms times QLHV. So this is the efficiency, and this is the result of the efficiency of the Sabate cycle. I'm sure many of you already did it in the past, but probably it's a good exercise to try to do it together, because it's the way to recap some basic concepts. It's the very first lesson, so it probably makes sense to take a few time to do it. So if we draw again the indicator diagram of the Sabate cycle, minimum volume at maximum volume. This is the pressure. And we say that here we have the intake pressure P1. We have an ideal compression. The combusting process is half at constant volume, or not half, but partially at constant volume and partially at constant pressure. This is 1, 2, 3, 3 first, and 4. So we introduce heat here, and we introduce heat here. We can name it Q1, which is split into these two portions. And here we discharge heat, Q2. So the efficiency, the thermal efficiency of the cycle, as you studied in previous courses, is the work divided by the total heat we make available for the system, for the energy system. And it is therefore equal to Q1 introduced minus the discharged heat Q2 divided by Q1, which is obviously 1 minus Q2 divided by Q1. Okay, easy peasy. So since part of the heat is introduced at constant volume and part of the heat is introduced at constant pressure, you will have that Q2, which is this one, is constant volume, so it is CV times T4 minus T1. This is Q2, divided by CP times T3 minus T2 plus, sorry, my bad, CP times T3 first minus T3. Okay. Imagine T1 is the ambient temperature. You see that this efficiency here depends on the specific heats plus some temperatures. Okay? And if we define two ratios, which are A, which is the ratio T3 divided by T2, and B, which is T3 first divided by T3, it is easy to calculate analytically the thermal efficiency, because from T1 you can calculate T2. Okay, we have an isoentropic compression. Which is P times V at gamma equal to a constant. Okay, so again this means that P1 at the beginning of the compression times V1 squared at gamma is equal to P2 V2 squared at gamma. We are interested in the temperatures, so we immediately notice that this, I'm sure you know it from the past, this is equivalent to T1 V1 at gamma minus 1 equal to T2 V2 at gamma minus 1. It's very easy to go from this to this because PV is equal to MRT. You just have to calculate the pressure and replace it with MRT divided by V. And the job is done. So based on this, we can immediately determine T2 as T1 times V1 divided by V2 at gamma minus 1. But if you look at this, you see that V1 is this volume here, so the volume of the combustion chamber plus Vd, and V2 is the volume of the combustion chamber. So this is T1 times VCC plus Vd divided by VCC. And what's this ratio you see here? This ratio is the compression ratio. Sorry, not everything. This one is compression ratio. So RC is equal to VCC plus Vd, so the maximum volume of the cylinder divided by VCC, the minimum volume. So based on this, T2 will be simply equal to T1 times the compression ratio at gamma minus 1. So T2 will be this. Very easy to calculate. And this is the compression ratio. So T2 is equal to RC, sorry, T1 times RC at gamma minus 1. What about T3? T3 is very easy. Before we introduced these two ratios. So T3 will be equal to A T2, so T3 will be equal to A T1 times the compression ratio at gamma minus 1. Okay. Again, stop me if something is unclear, because I go reasonably quick on these considerations because I think that they are more or less known to you. So we have T2, T3. We also defined another ratio before, B, which is T3 first divided by T3. So we can also write T3 first as BT3. So it will be equal to A B T1 times the compression ratio at gamma minus 1. And now we know T2, T3, and T3 first. So we know T3 first, T3, T2, T3, T1 was already known. We are only missing T4. So T4 is here, so it's at the end of an isentropic expansion, which starts from 3 first. So 3 first, 4 is an isentropic expansion. Let's write it here. So 3 first to 4 is an ideal expansion. So if it's an ideal expansion, it means that T3 first times V3 first at gamma minus 1 is equal to T4 V4 at gamma minus 1, which means that T4 is equal to T3 first, which is something we know, times V3 first divided by V4 at gamma minus 1. So this is T4, but the problem is that we know T3 first, it's already known, but we don't know V3 first, because look at again at the indicator diagram. We are going from 3 first to 4. We know T3 first, we know V4, but we don't know V3 first because it is here. So we need to calculate V3 first. To calculate V3 first, what can we do? We can have a look at where it is, and we can notice that it is exactly at the same pressure of V3. Okay, so if we consider the fact that P3 is equal to P3 first, so the pressure is constant, we can consider that since P is equal to mRT divided by V, P equal to mRT divided by V will be constant from 3 to 3 first. Okay. So this equation, P3 equal to P3 first, can be written as M R P3 divided by V3 equal to M R P3 first divided by V3 first. Okay, which means that this mass can be neglected. This can be simplified because R is the constant of the gas and M is the mass of fuel trapped in the cylinder, which is always the same between 3 and 3 first. Between 3 and 3 first, because the valves are closed. So what we can do is writing that in this case T3 divided by V3 will be equal to T3 first divided by P3 first, and we can say that B3 first will be equal to T3 first divided by T3 times V3. But we know what this ratio is because this ratio is B. We defined it before. We know V3 because V3 is the volume of the combustion chamber, so this volume becomes equal to BCC. So B3 first is something we know. Or better, we didn't know it, but we calculated it. Okay, so if we go back and take this result and we put it here, we can determine also T4. So, as a result, T4 will be equal to T3 first times VCC divided by V4, which is VCC plus BD at gamma minus 1. Okay, which is T3 first is, we had it before, is ABT1 times the compression ratio at gamma minus 1 times B at gamma minus 1 times 1 divided by the compression ratio at gamma minus 1. Okay, so this can be simplified with this, and we get that T4 is equal to AB at gamma T1 AB at gamma T1. Okay, and we also found T4. Okay, so based on this, we are able to put the temperatures in this initial equation of the thermal efficiency, and we can calculate it as thermal efficiency equal to 1 minus CV times, it was, remember it, T4 minus T1. So T4 is here, so it is A, B at gamma T1 minus T1 divided by CB times, it was T3 minus T2 here, so it will be A T1 times the compression ratio at gamma minus 1 minus T1 times RC at gamma minus 1 plus CP times, it was T3 first minus T3, so it is A, B, T1 times the compression ratio at gamma minus 1 minus T3, which is A T1 times the compression ratio at gamma minus 1. So here something can be easily simplified, because you see that T1, 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 and T1 can be simplified. So what we have here is a simplified equation like this. I also simplify this and this, and I divide this by CV. So I obtain AB at gamma minus 1 divided by A RC at gamma minus 1 minus RC at gamma minus 1 plus gamma, which multiplies AB RC at gamma minus 1 minus A RC at gamma minus 1. We can also collect the compression ratios, which are here, 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 and here. And we obtain the final expression of the thermal efficiency, which is this AB at gamma minus 1 divided by RC at gamma minus 1 times A minus 1 plus gamma RC at gamma minus 1 times AB minus A. Okay, and this is the thermal efficiency of the ideal Sabate cycle. Okay? And if you compare this with the expression that you had here in the slides, you see that the result you get is the same. You just have to collect this ratio, the compression ratio at gamma minus 1. Of course, here in the slides, K is Cp divided by Cv, so it's the specific heat ratio. I named it gamma in the notes, but it's exactly the same. If we take this expression and you set A, which is again T3 divided by T2 equal to 1, you obtain the ideal diesel cycle. If you set instead B, which is T3 first divided by T3 equal to 1, you obtain the Otto cycle. Because in one case you set 3 first equal to 3, and in the other case you set 3 equal to 2. So if you set A to 1, so 3 equal to 2, you have the diesel cycle, and if you set 3 first equal to 3, you have the Otto cycle. Okay, and this is, I'm sure, a result many of you already know, but it's something we will start from next time to do some important considerations about the design parameters which affect significantly engine efficiency during its operation. And we will start to, based on this, highlight some of the major weaknesses of conventional internal combustion engines which limit their use as sustainable, efficient power systems, both with sustainable and not sustainable fuels, which we know as fossil fuels. We haven't spoken yet about sustainable fuels, but we will do it later on. But the point is that now we are highlighting technological weaknesses of internal combustion engines which are related to this thermal efficiency, and we will do it next time, because today our time is over as far as I see. I don't know if you have any question at the moment about what we discussed. If we don't have any question, I think I'm pretty sure we will meet in person next Thursday, and personally I think that in any case I will be in class at the university and I will teach from there in Bologna, so but I'm pretty sure everything will be fixed because it was a problem to the heating system, so hopefully everything will be okay for Thursday and we will finally meet in person there. I don't see any question in the chat, so I would stop the recording now. Let's see whether it works or not.